Okay, so let us now prove the equivalence of PDA and CFL. So the first thing we will prove is that for any CFL there exists a PDA which accepts L by empty stack. So the CFL will be given and grammar. So if L is a CFL, so then we know that there exists a CFG, right? And we proved earlier that we can transform the CFG into Grayback normal form. This is GNF, right? And what was the form of productions in GNF? So the first symbol in the right hand side was a terminal. Okay, so this was the form. But when we proved this GNF form in the previous videos, we allowed this alpha to be a combination of terminals and non-terminals. So in our proof we allowed this thing, but the same proof also works if we just restrict this alpha to be a string over just non-terminal, so just variables. Okay, so you don't need to change anything. I mean, you just change this to this and the same proof works. I mean, you can go through the proof and nothing changes. So there's a worked out example there also. You will see that this alpha is only a string over variables. So and in fact they are quite easily interchangeable one version to another. Here it will be easier to work with if we restrict alpha to be just a string over variables. So now from this given grammar, so the grammar is not given, the language is given, and that ensures that there exists a grammar in GNF. So from this we will construct a PDA which accepts this L by empty stack. And how do we construct this thing? So the number of state is just the singleton thing. So this state will not be used at all. I mean, since this cannot be empty, we have to have something. So we just have one state. This will be irrelevant. So first of all, you notice that so the strings here in this L, so they are strings over this T. Okay, so one point of one thing is that in order to have this GNF, we stated that this L should not contain epsilon, because GNF doesn't have any epsilon transition. But without loss of generality, we can assume that this L doesn't contain, because if this L contains this epsilon, we can have this construction for this thing. So first we remove this epsilon from L and then construct a PDA. And after we construct this PDA, then we can add another epsilon transition such that the whole purpose of that epsilon transition will be to accept just this empty string. So yeah, so it is sufficient to prove this statement, assuming that this L does not contain epsilon. Okay, and we need this because GNF requires that this L should not contain epsilon. Okay, so once that is done, so now, yeah, so the strings are over this terminals T. So here the input alphabet is T, and here the stack symbols will be variables here. So we have this correspondence. You will see it immediately on why. So they are same. And then we have to construct this transition, which will depend on the production rules here. And again, so since the stack symbols are just the variables here, so the start stack symbol will be S. Again, there is a expected kind of correspondence, because here you start with the symbol S and somehow you generate the string in the language. And here also we start with S in stack, and somehow the stack grows and shrinks back, and after something you process the string. So in both cases the starting thing is this S. And since we are using this empty stack criteria, so the state of final state doesn't matter, so we just keep it phi. Okay. So now how do we construct this lambda, this delta? So that's the main thing. So you see, we just have this only one state. So as I said, the state doesn't matter. So you are in state q, and again you will be in state q. The only thing that is of interest is, so if you see this input symbol small a, and if your top stack symbol is say capital A, then how are you going to replace this A? And here we are replacing this A by gamma, where we have a production of this form in our grammar, which is in GNF. And since this is in GNF, we know that all the productions is of this form. So this will be a variable, this will be a terminal, and this will be a by this criteria. So this will be a string over just variables. So then this is a string over variables. That means this is a string over stack symbols, because these are the stack symbols here. So we are replacing this one stack symbol which is at the top by the string of the stack symbols. The state doesn't matter, and this is how the input symbol A is processed. Okay. And again, see, there's a correspondence here. When you are applying this production, so you are generating this symbol, right? So from this you are kind of generating this, and then you have to expand this. So this part will generate something else. So from the grammar's perspective, we are generating this symbol. From the PDA's perspective, we are kind of processing this symbol, and this should be there should be a one-to-one correspondence, because in grammar a string is in the language if you can generate that string. For PDA, a string is accepted if you can process all the input symbols and get to the empty stack. So the claim is that with this construction, this L that we started with, so that should be this n of m. That means the language accepted by this m by empty stack. And the proof idea is that this PDA m, so this simulates the leftmost derivation of G. So this is kind of already clear from the definition of this thing. So now just to make it more prominent, I'll just go through a example. So just take this example. This grammar is already in GNF. You see that the first symbol in the right hand side is a terminal, and the rest of the things are just variables, right? And so if we consider a leftmost derivation of say this string, okay, so how does it proceed? So now you first generate this leftmost symbol, right? So this A you have generated in the first step, and then you have some variable here according to this rule, and then again you expand this variable using some production, and since the productions are of this form, so you will generate again another symbol. So first you generated this symbol, and then from this B you are generating this symbol, and this B is being replaced by BB. So we are using this thing. Okay. So again this B is being expanded by this rule. So we are generating this symbol, and this is being replaced by this. So you already see that it kind of clearly shows how you can realize this using PDA. So you are kind of generating one symbol, and then there is a replacement of a variable by a string of other variables. So it is quite clear the corresponding moves here will be like so when you see S, and if you see A here, that means you have to match this S with something here which starts with A. So you look for productions here. So here is a production which has S here, and it generates this A. So this should be the thing. So that means this S should be replaced by B, and the state doesn't matter as always. And here you see this should be a set of pairs according to the definition of PDA transition function, but here everything will be singleton. So here in fact not okay, for this grammar it will be singleton, but suppose we also had some S going to A and something else, say AC. So in that case, this delta QAS, this will also contain this, say Q. So Q will always be there, but here this S is being replaced by C. So this will also be included here, but this grammar kind of for this grammar we get this singleton sets, but the singleton is, in general, it will not be the singleton thing. So anyway, so that means, I mean, from this example it is clear. So if you see the corresponding thing that is happening in M, so it has all the inputs, right? So it is generating this A, and correspondingly so it is reading this A here, okay, and then it is replacing this S with B. That means this S is replaced by B in the stack, right? So these are IDs, okay, and this Q is irrelevant, and then it is looking into the second character here. So this is A, and in this case, so as I said, I mean, it again has to replace this B by something where it should generate this A, and so that means B goes to A something. So yeah, this, and the corresponding thing is here. So this B is being replaced by this BB, right? So if you go through this example, so just stop the video, pause this on this slide, and go through all the steps and match these steps, and it should be quite clear that the thing that we are doing is just this. So if we have a production like this, so that this goes to terminal and bunch of non-terminals, so that means we are actually replacing this stack symbol this with this bunch of non-terminals, and this is being consumed. And if you want to prove this formally, then you just have to do a induction over the number of steps. So you prove that in I many steps starting from this ID. So what is this ID? Again, the state is always Q, doesn't matter. The input is X, start symbol is S, and from here it has consumed all the inputs. So the remaining input is epsilon, and now the stack contains some symbols which together is just alpha. So alpha belongs to this V star. So if this happens in your PDA M, so then the corresponding thing that happens in your grammar is that in I many steps, so in grammar G, you are deriving this XA, like so this you have generated. Here you have processed this X, and here you have generated this X. So X is a string, right? X is a string over this T. So you have generated this X, and then so this stack thing corresponds to whatever you have after this. So that means you will have to somehow expand again this thing to kind of extract all the input symbols. So the and how does it say that this language is equal to this? Because then again, if you just replace this alpha by epsilon, so this means that this X is accepted by empty stack. So when is x accepted by empty stack? If this becomes epsilon and again this becomes epsilon, right? So for a special case where this is epsilon, so that means this goes to this x epsilon, so then that means this goes to x, that means s derives this x. And this happens in both ways. So first you prove that this implies this and then this implies this in I many steps. And the basis is simple. For 0, this two part will be same. So the only way this can happen is if this x is equal to epsilon and if this alpha is equal to s, right? So that means you haven't given any input and you haven't executed any steps, so number of steps is 0. So that is trivial. So to complete the induction, so for this direction, so then if this is not epsilon, it contains at least one symbol, so this x will be of form ya, where this y can be empty, so this y is a string, but this a is a symbol, right, in T. So, and how can this thing happen? So first it has to process all this symbols in y, okay. So then at the last step it processes this a. So what happens is from here in some I minus 1 many steps it has processed everything here, and then after that it has something in its stack, okay. So and the top stack symbol here is a, right. Again and then in the last step it sees this input symbol a and it sees this top stack symbol a, this capital A, and this is being replaced by this gamma, okay. And this happens when we have this pair in the transition of this QA capital A, okay. So that means here this alpha is just this gamma beta, okay. Now this thing implies by our construction, so since this was our construction by definition of this thing, this delta, so this means that we have a production of this form, okay. So this implies that we have a production of this form, and by induction hypothesis, since this takes I minus 1 many steps and we are doing this induction on I, so for this I minus 1 many steps, it implies that in I minus 1 many steps in the grammar also we can reach this thing. Why? Because if you just match the terminals and the non-terminals, so it has processed this y part, right? So in fact okay, so this implies this, because see how does it process this thing? So you have given this ya and it has processed this y part, right? And then the stack becomes this. So instead of this ya, if you just give it y, okay, so then this a will not be here. So after processing y, this will become epsilon, right? So if you just give y here, so then after processing this whole y, so nothing will be left, so this will become epsilon, and the stacks will behave similarly, so all the intermediate things. So if you consider all the intermediate IDs, the only difference is that in case of this middle part, you will have this extra a here, and here you will not have this extra a. The stacks will be exactly same for all the intermediate IDs, okay. And yeah, so then by this induction hypothesis for this I minus 1 step, so we will have this, right, because this y is consumed, so this will correspond to this, and then this stack is in this form, so it will be this. And now if we put together these two things, this and this, so after just one step, so from here we get to this place, and after this, just in one step, this A is being replaced by this A gamma, right? Because we have this, and this Ya is just X. This Ya is X, and this gamma beta is alpha, right? So this part is done, and the other direction is also just the same. I'm kind of read in the opposite direction. So if you can do this in your grammar in many steps, then you can do this in your PDA also in many steps, and you see that again. I mean, this you can break down and break it down in this form. Again, this X is just Ya. So since we are talking about leftmost derivation, so that means it has to first it has to generate the symbols of X from the leftmost side, right? So from starting from S, it has generated all the symbols except this last symbol A. So X is A. So at this stage, it has generated up to this Y part, and it has something here. And since the productions are of this form, this A is going to some terminal and then some bunch of non-terminals. So at each step it will look like this, a bunch of terminals in the beginning, and after that you have a bunch of non-terminals. You won't have a mix, right? So you can see it from this example. At each stage you have a bunch of terminals and followed by a bunch of non-terminals. So this happens because we are using this GNF form. So after I-1 many steps, you are in this form, and finally you replace this A by this small a gamma. So you get this Ya as X and this gamma beta as Xa. So this has to be the derivation for this thing in your GNF form grammar. So this must be a production in the grammar. So then this means that you have this pair in your delta. So that's by definition of our PDA. And again by this induction hypothesis, for this I-1 many steps, we have this, right? Because this ensures that this happens. So that means so if we have this, then it ensures that this happens. And again, we are just going from doing it from the other direction. So here we argued that if we have this, then we have this. So that means here we have this extra A all along this I-1 many steps. So we can remove this extra A to get to this thing. So here we have this, and now instead of Ya, if we consider instead of Y, if we just consider Ya here, so Ya here. So that means again all the intermediate IDs will be same, except for the fact that here whatever we have in the place of this remaining input, here it will have extra A at the rightmost position. So instead of this epsilon, you will stop at this A and the same stack string here, and then from here you can apply this thing. And this happens because we have this production, which implies that we have this pair in our delta. So we have this single step transition between IDs in M. So after this, so after we go here, we can do this thing and we reach here, which is this thing. So this is done. So you see that if you have a CFL, you can consider the GNF grammar for that CFL, assuming that your language doesn't contain epsilon, which can be tackled later, and then from that GNF you can easily simulate the leftmost derivation using a PDA. So this is the idea.